Welcome to this week's Graphics Programming Virtual Meetup. We follow the Berlin Code of Conduct. We have a Discord, which some of you were talking on beforehand, and you can join. And then a Twitter you can follow where we announce meetings. And a YouTube channel that we upload the lecture-y part of the meetings up to, so people who missed it can watch it later. This week we're going to be talking about the Homogeneous Perspective Transform, an article written by Jim Blinn in his Jim Blinn's Corner. Date is around May 1993. I put the date there just to signify what year this is happening in. There's a link to it. Can I copy paste? I can. Let me do that. So if you want to look at the paper itself and marvel at its diagrams without the screenshot I took of it pasted here, that'd be okay. So what is a perspective transformation matrix? If anyone who isn't very familiar with the rasterization graphics pipeline, it's a matrix that transforms things from camera space into screen space, device normalized coordinates. It's the thing that skews the scene into looking like it's a perspective view rather than a flat parallel lines are perfect view. Specifically, it is a non-affine transformation, and that does make it a bit harder to intuit. So what is affine? Before we can say what non-affine is, let's talk about what affine is. An affine transformation matrix is one that preserves the collinearity of the output points, in that if there are points on a line, when you apply that transformation matrix, that line is still going to be the same, even if it's rotated or scaled a bit. The other is that the ratio of distances stay the same, so that when you do scale a line or rotate or whatever, that midpoint is still going to be the same ratio distance between it. All of your bog standard building block matrices, translation, rotation, scaling, and shear, they're all affine. And one way you can tell an affine transform is for a 4x4 matrix is that the last column has all zeros and the O for everything except for the last variable, which is, or last last place, which is the one that you'd find in an identity matrix. So it's effectively a zero does nothing row to the output. Non-affine is really a superset of affine transformations, so it's not binary. What non-affine matrices do is they do not preserve the ratios of distances. So when you when you apply the matrix, it moves that midpoint around to where it's not a ratio of the same distance between it. It could skew it to the left or to the right or anywhere. But it does preserve collinearity, so the lines will still be the same. And you can intuit that by imagining perspective, just how perspective works in real life and how the lines are still there. It's just receding into the distance or getting small, whatever. The way you can tell these apart generally is the lack of a 0001 in the last column. And that's because that's where all the perspective stuff happened, or all the specific stuff to non-affine transformation matrices happen. To actually explain what all is going on, we need to understand homogeneous coordinates. Homogeneous coordinates, as Wikipedia says, is this long quote which you can read and find out it is descriptive but not very obvious what it all means. A homogeneous coordinate in layman's terms is always one dimension higher than the space that you're wanting to represent. So if you want homogeneous coordinates for 3D, you need 4 variables, and if you need it for 2D, you need 3 variables. And since we're doing 3D graphics, we're going to be using X, Y, and Z. So we tack on an 0 value, or we tack on an extra value at the end, and that gives us a homogeneous coordinate. But specifically, when we say tack on something to the end, we're really meaning there's always been a 1 at the end of it, which is the W value. It's just now we're representing that in a 4 vector segment instead of a 3. And that W value is what gives homogeneous coordinates its homogeneity, for lack of a better word. When you want to transition between a, what I'll call Cartesian, or just real world coordinate, to a homogeneous coordinate, those three real world values are the three real world values, and then you tack on a 1 on it, and that gives you a homogeneous coordinate. But that's only because there is an invisible factor at the front of those x, y, and z. Because homogeneous coordinates, each Cartesian coordinate has an effectively infinite number of homogeneous coordinates that represent it, because there's that W scaling factor at the front of it. Specifically, I forgot to mention that while going down this explanation, that the way you go between the two, between Cartesian and homogeneous, is you divide by W, and that will, you take the fourth component and you divide the other three components by that amount, or by that value, and that returns the value into a Cartesian one, but it's really, you're returning it into a xyz comma 1, as in it's in the 1 plane of the W space, or the fourth dimension, because it's a 4-dimensional number. So that's enough blabbering on about that. The cool thing homogeneous values do is that we can represent infinity in a concrete value, because we can have a 0 for the W coordinate. And this 0, if you try to divide the x, y, and z by, well, it's really undefined. But if we take the limit as W goes from 1 to 0, you'll see that the x, y, and z values increase and increase, because if you divide 1 by 0.1, you get 10, and if you divide it by 0.01, it gets 100, and so the limit as you approach, well, 0, the x, y, and z values go to infinity. And that's really rather useful because we can do math with it. Yeah, so that's how you can understand that there's infinitely number of values, because that W factor is being divided across the other ones. So it's really cool that we can represent infinity with normal numbers, rather than having to write the infinity sign every time we want to do something with it. The interesting thing, though, is what that means for the space we're in. If we look at what happens to W as it approaches 0, we see that, it gets much larger, but at the same time, if you flip the sign on it, it will also go flip to the other side in sort of Mobius strip-like fashion. Similarly, that implies that as you take a point out to infinity in one direction, say A or B or any of these values on the chart, that value will have effectively the same coordinate as the negative one of that. So -1 and 1 on the x-axis taken to infinity would be the same point. The way to illustrate that is this chart here, which, if you look at the original PDF, you can't really see the different gradations very well, the different hatch marks, and because it's a binary digital scan, it totally loses that detail. So the things to note here is that these 3 lines are connected at infinity, but notice the colors red switch between these sides. So as you're going from here, say, if this line segment, it wraps around to infinity, but the color on the right side went from green to red. So it's quite, because like if this is point A and this is point B, then the line segment here is A to B, but if you do the inverse of that, you do B to A rather than the direct inverse. Anyways, the space is infinite and Mobius, and it's weird to think about, and I can understand why people have a hard time with it. The author, Jim, describes that there's 4 places that we can consider coordinates to be in. There's only 2 spaces, which is the Cartesian and then the homogeneous spaces. But when dealing with perspective transformations, it's useful to distinguish 2 subphases. So we have our 3D coordinate that's just in Cartesian, and when we tack on a 1 onto the end, we've turned it into a homogeneous coordinate, but the value of the x, y, and z hasn't changed. I mentioned earlier, but you can picture this as being the w equals one plane in hyperspace, that hyperplane in 4D space. I've been watching too much Star Wars. So when we perform our perspective transformation, we now have a value in a homogeneous space where the w is not going to be equal to 1. This means it's a 4D value. The way we can transfer that back into the 3D Cartesian world is divide the w out of it, so you get a 1 again, so you can just cut it off, because that's the identity of sorts. So we have the 3D, 3DH, 3DHP, and 3DP. So 3DH and 3DHP are both in homogeneous space, but with the P's represent whether it's after the perspective transformation or before it. And this is a good thing to distinguish because it explains some of the weirdness with the GPU pipelines. So it's good to start with the basics, where we can do a lot of math with just a diagram here that represents projecting a point in 2D onto a 1D line, this Y line here. Similarly, you can do this on the x-axis to get a whole nother axis, but looking at the y is very helpful. So when we're projecting the point y, z onto the y-axis, that isn't confusing, we can look at the ratio, as in the angle between ys and t over y and this line here. And notice that it's going to be the same ratio, because this is, even though this is further out, this is going to be the same amount as tall. It's a ratio. So we can use that to, well, start doing our math. Our y over d, as in the line segment here, is going to be equal to the y over this entire distance. Since we have y here, that means this is the 0 value. Oh wait, no. This is the z-axis, and we're defining the this vertical line to be c equals 0. So to get the total distance, we just need to take d and add it to z, and then we divide that, or we divide y by that, and then we have our ratio between the two. And this d value here represents the distance from the image plane to the eye point. Usually that's assumed to be 1, which simplifies a lot of things, but it doesn't have to be, and I appreciate that the paper doesn't explicitly define it as 1, because it allows for a little more nuance. So we have our two ratios. We can then move the d over, and there's a bit of algebra going on, but we can pull the d out of the bottom, so we get the z over d plus 1 as our denominator, and that will cancel out with the d above it to leave us with y over z divided by d plus 1. So this value here, this height value, could be computed just with this y value and the z and the d, and that will give us our projected value. And interestingly, because of how the homogeneous coordinates work, we have also the ys is equal to a little ys over ws. So this is our 3D Cartesian, and this is going to be our, this y here is going to be our homogeneous y and homogeneous w. And we can see that to get from ys into Cartesian, or yeah, to get from homogeneous ys to Cartesian ys, we have to divide by the w, but we can see that the ratio is equal here. So if we can say that ws is equal to z over d plus 1, which gives us this homogeneous coordinate, homogeneous vector, I guess, x, y, z, and then the w value of z over d plus 1. So when we divide the rest of these values by the w, we get our Cartesian value out of it. This is where the math started losing me, because the way it was described didn't really jive with how I've learned about homogeneous matrices and homogeneous coordinates and perspective matrices. I get what it's trying to go for, and this looks like what I studied and remember, but the actual matrix here, it was not obvious how it got from A to B to C and then to Z at the very end. So while we could do this funky algebraic computation, we can also transform that into a matrix, and then we can simply multiply a matrix by our coordinates, and then we get our homogeneous coordinate output. The thing that's missing here is that this says it's in P space, which if we go back to here, we have this P here. That implies it's in Cartesian coordinates. But there's no explicit divide by W going on. So that's something that I think is going on, but I couldn't intuit from what the text was saying, which is ironic because this paper is about how to have an intuition about the perspective transformation. Anyways, when you multiply this homogeneous coordinate by the perspective transformation, you get x, y, z as the first three, and then the W value is going to be, I believe, 1 times 0, 1 times 0, 1 times 1 over d, and then 1 times 1, and then matrix multiplication. That means you add all those things together, which gives you 1 over d plus 1, and then you use this to divide the x, y, and z to get your actual Cartesian value out of it. And that's important because, well, that's the math. It's important because it's important. Now, the thing I want to point out is that since we're going to be dividing all three x, y, and z values by the 1d over 1, where does the z come in? Someone has a mic echo, or at least for a very split second. See, this is why I was confused by this, because I'm not seeing where the divide by z comes in for the x and y axis. So I copied this correctly, didn't I?
Well, because it's row major, so it's really hard to read. But yeah, yeah. If you mentally translate everything, well, sorry, not translate. What's the word? Like
flip.
Transpose. Yeah.
There we go.
Yeah, it's just if you mentally transpose that, it will be much easier. So the z comes from that VOD term times z, and you add that to W.
Yeah. Some of these things I get the gist of, I just can't tell you the exact math, and I don't think it'd be right for me to assume I could, because, yeah. Anyways, some of the observations, continuing on, some of the observations made are about the z coordinate, where the x and the y coordinate are pretty, they get divided by z. What the actual z values do is kind of interesting. The illustration here is a fence post line, a picket fence, I mean. And we have an eye point here. The interesting thing is the scaling that happens to the little lines as it goes into the infinity, but then there's this reversal backwards, and that's due to that weird flipping of space inside out due to the Mobiusness of the space. So some of the observations were that if you have a 0 value and a 1 for the W, it stays there, which is the plane at z equals 0 remains, which I believe would be this y-axis here, or y line. But if you have it at -1 over negative d, so where the eye point is, it will, when you do the divide by W and all that good stuff, you'll get a 0 value for there, whereas the negative d is still there, but because the W value is 0, it's at infinity, which is a weird thing to imagine. And here we have the infinity point, and it will move back into the finite range with a W value of 1. And just trying to imagine space inverting in on itself and then going to infinity as it's doing that is wacky. This is the chart that took me the longest to kind of get a grasp as to what it's doing, and I appreciate some of the images that were linked in the Discord, because that helped me see what was going on, because this is not nearly enough, and it's be lovely if this could be animated. And I tried to copy and paste the animation I saw in here, but unfortunately I don't pay for slides, so I don't get video access. Anyways, the description is that a perspective transformation is simply a shear in the W dimension, which is not like the idea I had in my head of a non-affine transformation being hyperspace and all sorts of crazy math. It really is just you go up a dimension, you shear, and then you go back down a dimension, and now your thing's transposed as if it was done by a projection. Well, not as if, but as it was done by a projection. So we have over on this side, we have our homogeneous coordinates. So everything's at W equals 1. We shear, as we can see the W value of this W, the values form a line that is no longer at W equals 1. And then when we want to move back into the Cartesian space, we have to divide by Z and it will project all these values. Now, the reason it looks weird is because I'm seeing vertical lines and then I see these lines that go weird places, and that's because it's not a projection downwards. It's divide by W. It's getting the Cartesian values out of that after you've sheared it. So it's not the projection is actually happening here, not in the latter step. And I think that's what confused me at first. The paper also notes how Z equals 0 and Z equals infinity move. We have Z equals 0 stays in the same place, but it's noting that Z equals 1 does not stay at infinity. Or does it? Wait. Okay. I need to look. Paper says, note how the I point Z equals 0 point and the other point transform. Oh, okay. It doesn't tell you exactly what's going on. Okay. Well, I'll leave you to read the paper to get final understanding. We have this one-dimensional transform where we're only looking at the z-axis. I think points, the Chen asks, are points behind the eye being reflected around 0? I think reflected is the wrong term because it's not like a multiply by -1 kind of thing. At least that's how I think about it. If that's, I couldn't say for sure though. The diagram here makes it a little clearer what I've been mentioning, where we have our 2 dimensions, our z and our x. We can see on our homogeneous coordinate, everything lies in this W equals 1 plane. And then we project it in this W dimension, which is, as you can see, it's really a shear. And then when we divide by W, that's when we project it back into that W equals 1 plane. Project, it's not the right word. Put it back into the W equals 1 plane, and it then gives the shape as you want it to, which is the perspective, diminishing, size diminishes as Z increases. And there's another good image that is kind of just the 3D output of this, where you have the Cartesian input and the Cartesian output, because there's no homogeneous coordinate visualization here. And this is what I imagined a perspective matrix to be, but I didn't quite get the whole jump into the hyperplane and going through that whole process to get us to this. I just imagined it was kind of just squishing the sides and back and flattening, and that was it. And it wasn't quite as simple as that. So the other thing is that if you look at rasterization algorithms, they're trying to take a 3D shape and get it to where you can do a 2D flat plane out of it. But the perspective projection is not a flat projection. It is a 3D projection that happens to go into a cube. And this cube, well, sometimes called the device normalized coordinates because it goes to, -1 to 1 on each axis. This cube can then be easily flattened out when you do the rasterization itself, but it's very handy to have this cube. At least it looks like a cube in my head, even though I understand it's not exactly one, because the clipping algorithms work really well if you do them in homogeneous space, because then you are, when you clip, anything that's bigger than W would be outside of that range. This paper doesn't talk about it in detail. I was reading the Scratch Pixels articles on that, and that's described why homogeneous space clipping is a thing and why it's nice to have. And then once you finish clipping it, then it's the perspective, that the divide by W happens, getting you an actual cube that you can, then your raster algorithms can flatten out. That I've heard it described as like, it's like an ortho, once you've completed the perspective divide, going to the flat plane that you want to present to the user is a bit like an orthogonal projection, because the pixels at any given pixel, they're the the z-axis as it goes into the scene is straight. There's no deformation there. I'm not sure if it would be correct to call it an orthogonal projection, but it feels similar. So that's the thing that this paper has in its date, and I mentioned the date is because it predates, I was about to say modern fixed function pipeline, which sounds like an oxymoron, but it predates the 1995, 1994 beginning of fixed function hardware being in consumer GPUs rather than only in big silicon graphics workstations. And I'm assuming that those big workstations worked similarly, but the point is that even though this paper predates that pipeline, it doesn't really impact the actual math going on. And when we look at the later GPUs, the programmable pipeline ones with vertex shaders and other things, the same concepts still apply. We just implement it differently. Where how we define I believe when I was studying, quick aside, when I was studying perspective matrices for the first time, when I was trying to implement them in a game engine, there were several articles I was reading talking about the differences between fixed function and programmable function pipelines. And as far as I can tell, the math is the same in both. And even the implementation doesn't really differ that much, because the APIs are so different that of course they're going to be different to implement. They're just done in a different way. And so that really confused me. And I think I was using that knowledge I vaguely remember to read in this article and get things wrong while I was reading it, understand things incorrectly. So when a GPU, to get back into it, when a GPU vertex shader or the fixed function pipeline computes the position, it first gets it in homogeneous space before it does the clipping, and then it divides by the W to return to the user, or not to the user, to the fragment shader. And the person responsible in a fixed function, in a programmable function pipeline, is the programmer writing the perspective matrix. And that's where I think the confusion came from, because the way you define the perspective matrix in a fixed function pipeline was a lot more strict. So your shader's perspective matrix should leave the W as a non-1 value for the GL position or your vertex output, but all of the other attributes that you have in your shader, your normals, your texture coordinates, any other things that you want to pass between the vertex and fragment shader, those shouldn't have a W value of non-1, because those are not going to have the perspective divide done on them.
Wait,
So
you mean 0 or 1?
They should be 1. Okay, now I'm confusing myself.
Yeah, I guess one is just nothing. Yeah.
And if you look at Rasterizers, where they have the perspective divide explicitly done by CPU code because it's a CPU software rasterizer, there's some interesting stuff with having to interpolate vertex colors, normals, and texture coordinates, because if you try to interpolate between the values out, you get from your perspective matrix, you're not going to be able to do a simple linear interpolation because the definition of non-affine transformations is that the ratio doesn't stay the same. So a linear interpolation would not be correct. This is the, I think, most complex, but supposedly the most telling diagram of the entire paper, showing the movement of different spaces around the scene. Unfortunately, a lot of these dotted lines were lost due to that bit scanning, and it makes it a little harder to read. The pertinent details are, however, the frustum defined by the angles here, and how it's currently a box over here, and that's just because it's a projection and it's turning it into a box is what you want. But notice the movement of the areas on the other sides where we have A and B are still here, but A is actually all the way behind the camera, whereas the B is the viewing, B is the area that we're actually looking at, because I believe the YS line here is our viewing plane. So anything behind it is going to be, well, clipped because it gets put at near at negative infinity. The other thing is the reversal of the G, C, A, F. We get F prime, C prime, G prime. And that goes along with the Mobiusness, where we're wrapping around to the other side completely, as in where the G and the G prime are opposite in the from the 0, 0, 0. And so, yeah, this is the culmination of all the weirdness all into one image, and that is unfortunately harder to read because the picture quality is not great. One thing I won't go into detail because this talk has already gone on long enough is all the little details to determine the left, right, top and bottom, and near and far plane, because the perspective transformation is an operation that happens, but whether you want it to be a little wider, a little narrow, a little taller, a little shorter, those are just scaling factors effectively. And you can compute those and you can derive those and put them into the matrix like we do over here. If we want to have a field of view, we need to figure out the field of view, and the sign is the depending factor on it. And so this is where the Pareto principle comes into play. This is 80% of the work in terms of all the math going on, but the understanding of it is not, understanding the principles behind it does not require a lot of this stuff. And my last slide, because I really like to reverse C, is that the paper talks about you need to be careful about your near and far planes, because the reason we map Z values to 0 to 1 or negative 1 to 1 is for increased precision, because that's the floating point values. Unfortunately, there's not nearly enough precision in that range to effectively describe your entire viewing area. So you have to choose your near and far plane appropriately so that you're not getting Z-fighting inside that range. Except in the last 27 years since this article was published, a thing called reverse Z happened, where we thought, what if our scaling factor that brings everything into our 0 to 1 or negative 1 to 1 box, what if we kept going and inverted it so that things in the far distance actually go to 0 and then things in the near go to 1? And it happens to be a bit of a hack, but it's based off the way floating point works, and it gives you way better precision, and it could be its own talk because it's really quite interesting how it works and the numerical analysis you can do on the actual values. This image actually comes from this week's weekly Graphics Programming Weekly. It's a Twitter thread by Eric Langlell in his book. So this is from his book, and it's actually a great visual representation of what's going on, even though there's some other articles that do a great job anyways.